Okay, let's dive into this. Have you ever looked at the fundamental numbers that govern our universe and wondered, why those exact numbers, right? I mean, the speed of cosmic expansion, the strict limit of atomic fusion, the fact that there are exactly 3 generations of particles. These numbers often feel completely arbitrary. It's kind of like someone just rolled a cosmic pair of dice and that was that. But what if the universe's most confusing, disconnected empirical numbers are actually strict, unavoidable geometric rules? Well, welcome to this explainer on vacuum elastodynamics. It's a fascinating framework proposing that the vacuum of space isn't an empty void at all, but rather a rigid geometric supersolid. We are going to explore how one single unified geometric concept might just explain the absolute boundaries of reality itself. Here is our roadmap for this explainer. We'll start with the free parameter crisis, then look at the elastic vacuum solution. From there, we'll zoom from macro to micro, covering cosmic friction, the limits of atomic nuclei, and particles as geometric defects, before wrapping up with a universe of geometry. Section 1. The free parameter crisis. The problem with arbitrary empirical inputs. So right now, our most successful scientific models, think the standard model of particle physics or the lambda CDM cosmological model, they have a glaring vulnerability. They rely heavily on arbitrary empirical inputs. You measure a constant in a lab, you plug it into the math, and boom, it works. But the math can't actually tell you why it works. The Vacuum Elastodynamics framework, or VED for short, presents this awe-inspiring alternative. It suggests that physical boundaries aren't just random inputs we have to go out and measure. Instead, they are strictly emergent geometric necessities. Basically, they are physical limits dictated by unavoidable math. Section 2. The elastic vacuum solution. The universe as an E8 supersolid. To fix this crisis, VG models the vacuum of space not as nothingness, but as an invisible, multi-dimensional crystalline lattice, an E8 supersolid. And because it's a structured lattice, it obeys mechanical rules. So the crucial point is this concept of tensor capacity saturation. Imagine an elastic band. You stretch it, and it beautifully absorbs that strain, up to a certain point, right? Once you literally run out of physical material to stretch, the band yields. It either snaps or permanently deforms. In this framework, whether we're talking about a single atom or the entire cosmos, a system remains stable only until the strain put upon it completely exhausts the available mathematical degrees of freedom in its governing geometry. Once the math runs out of room, the physics is forced to undergo a phase transition. Okay, Section 3, Cosmic Friction at the Macro Scale, General Relativity and the Hubble Tension. Let's zoom way out to the largest scale. Here, gravitational strain acts as a continuous stretching force on this cosmic lattice. Think about standard general relativity for a second. It operates via the Einstein field equations, which famously consist of exactly 10 independent differential equations. Why 10? Well, the VAD framework gives us a stunning geometric answer. Because the macroscopic vacuum operates as a 4-dimensional continuous solid, its elasticity is governed by a 4-dimensional symmetric strain tensor. And if you actually calculate the independent degrees of freedom for a 4D symmetric tensor, it mathematically equals exactly 10. No way, right? The 10 equations of gravity aren't an arbitrary construct. They perfectly match the exact saturation limit of the geometry itself. But what happens when the universe expands too far? As the Hubble expansion continuously pulls and pulls on this cosmic lattice, strain accumulates. According to the source material, at exactly a cosmic redshift of roughly 0.641, the expanding global lattice finally hit what solid-state mechanics calls the Frankel yield limit, basically its absolute breaking point where it ran out of elastic capacity. At that precise moment, the entire cosmic vacuum transitioned from a frictionless elastic solid into a yielding viscoplastic fluid. This phase transition is incredibly important. By yielding into a fluid state, a macroscopic friction was suddenly activated across the entire universe. This late-time lattice friction natively acts as a kinematic brake on local cosmic expansion. And this elegantly solves the much-debated Hubble tension, that stubborn discrepancy between early and late universe expansion rates. It solves it purely through the geometry of friction, without needing to invent mysterious new dark energy scalars. Let's move to and see how this builds. Section 4. The limits of atomic nuclei at the mesoscale. The geometric derivation of the viscoplastic yield event. We're zooming in from the vastness of the cosmos down to the dense core of dying stars. Here, protons and neutrons aren't just probability clouds, they're extended strain defects tightly packed into the lattice.
To minimize energy, they arrange in concentric coordination shells. But the four-dimensional vacuum can only support a maximum of exactly 4 independent harmonic radial modes. So the core holds 1 nucleon. The first shell brings it to 13, the second shell caps at 19, the third brings it to 43, and that fourth geometric shell perfectly fills at a cumulative maximum of exactly 55 nucleons. The lattice can elastically envelop 55 nucleons completely safely without fracturing. But watch what happens when you add just one more. To accommodate that 56th nucleon, the physical strain envelope is forced to create a 5th radial shell. But remember, the macroscopic spacetime metric fundamentally lacks a 5th orthogonal degree of freedom. It literally cannot harmonically absorb this added strain. So the localized lattice bonds physically rupture. And just like that, you natively derive the iron 56 limit, the exact thermodynamic dead end of exothermic stellar fusion, purely from solid-state geometry.
Now, what's really interesting about this slide is we can actually go even further to reach the ultimate absolute binding peak of atomic matter, nickel-62. When the lattice ruptures at 56, the nucleus doesn't just instantly fly apart. It enters a yielding fluid-like state governed by a three-dimensional symmetric stress tensor. And mathematically, that possesses exactly 6 degrees of freedom. By adding those 6 yielding degrees of freedom to the rigid elastic limit of 56, you hit exactly 62. The empirical binding energy peak of nickel-62 is perfectly reached just by adding the geometry of the vacuum.
Section 5. Particles as geometric defects at the microscale. Topological boundaries of the quantum realm. Zooming in one final time to the microscale, quantum particles are modeled as localized topological strain defects. Essentially, they're tiny knots or twists trapped within the lattice. And this explains a lot, actually, including the massive hunt for dark matter. For a lattice defect to act as invisible dark matter, it has to perfectly shield its strain footprint so it doesn't leak any radiation. To close this geometric envelope, it must fully saturate the 8 microscopic vertices of its local lattice cell, saturated by the fundamental lattice bond energy, which the framework identifies as the 125 GeV Higgs mass. This requires 8 times 125. That gives a strict lower mass bound of 1.0 TeV. If a particle is lighter than 1 TeV, it simply lacks the energy to independently pin those 8 structural nodes, meaning it would leak standard radiation. And what about the mystery of why there are exactly 3 generations of matter? Why is there an electron, a muon, and a tau particle, but absolutely no fourth? Standard physics kind of has no mechanism to explain this. But in the D4 lattice geometry, there's an internal symmetry called triality. Triality dictates that there are exactly 3 exhaustive orthogonal topological permutations possible for these defect alignments. A 4th generation is mathematically physically prohibited. The geometry contains no 4th spatial representation to couple to. If you try to force a 4th generation in, the math simply breaks down, causing the structure to shear apart. And this brilliantly illustrates the vast difference between different types of particles. Look at heavy quarks versus ultralight neutrinos. Quarks are heavy, high-strain defects. They are tightly gripped by the lattice, meaning they hop rigidly from point to point. On the other hand, ultralight neutrinos aren't confined at all. They just glide through the lattice as unconfined wave slips with almost zero friction, fluidly shapeshifting as they travel. Because this vacuum lattice was frozen with a strict geometric handedness, or chirality, during the early universe, a neutrino traveling through it is basically facing a one-way street. Therefore, it is topologically impossible for a neutrino to act as its own antiparticle. This beautifully dismantles the need for hypothetical, unproven heavy particles to explain why neutrinos are so incredibly light. Their tiny mass is natively suppressed just by how they geometrically smear across the hyperuniform lattice. Finally, Section 6, a universe of geometry, the scale-invariant blueprint of reality. So what does this all mean? Vacuum elastodynamics replaces dozens of arbitrary scientific parameters with literally one unavoidable rule: tensor capacity saturation. Whether you're looking at the expanding edge of the observable universe or appearing inside a single proton, reality is governed by this exact same geometric necessity. And I want to leave you with a final, kind of provocative thought about how a universe built exactly like this might actually end. Standard models sometimes predict a big rip, where some phantom fluid just tears space-time apart. But if the universe is an elastic geometry, we face what the source material calls the big flip. Eventually, the macroscopic tension of our expanding cosmos might mechanically overcome the fundamental electroweak binding energy. So instead of tearing space, the universe would simply untie its topological matter knots, unraveling reality back into a frictionless, uniform superfluid. It is a completely stunning geometric destiny for a universe defined by mathematics. Thanks so much for joining me on this explainer, and keep questioning the geometry of everything around you.